You can all see my screen.
Yes.
Yes, this is perfect. As you already said, my name is Moholwa, and I'll be presenting a project titled Decrepitation of South African Manganese ore during a pressing process in a rotary kiln. This will be the layout of my presentation. Firstly, I'll go a little bit into the introduction about manganese and the background of the project, and touch a bit on literature review, go into my method, discuss the result, and analyze the result and do the discussion. Then finally, I'll do the conclusions. This is the introduction. Manganese ores are widely used in the production of ferromanganese alloys. And a large portion of this produced ferromanganese alloys is consumed by the steel industry, seeing that this manganese imparts good properties to stainless steel. And globally, we have around 810 million tons of global manganese reserves, and 32% of this 810 million is located in South Africa. Manganese ores are generally produced in a submerged arc furnace, abbreviated SAF, and these furnaces are generally circular in shape with 3 electrodes located equilateral from each other. Then we get into PREMA. One may ask, what is PREMA? PREMA is a Horizon 2020 project aimed at reducing energy consumption and CO2 emission through proposing innovative technologies that will help to reduce this energy consumption and the emission of CO2. Then PREMA decided to tackle the production of manganese processes. This process sheet here is the current process that we use to produce manganese ores, manganese alloy. We have manganese being fed into the SAF with coke and some fluxes. Then we add electrical energy to melt this stuff. Then we get the product which will be Mn alloy, some gases and the slag. Then PREMA proposed adding a preheater to this current process of producing manganese. Then the process then looked like this. We have a manganese ore which is being preheated in a preheating unit, maybe a rotary kiln, a shaft kiln, but in this case we'll be focusing on the rotary kiln. Then we have this preheating unit being provide energy from a sustainable source of energy, maybe solar, maybe wind energy, maybe hydro energy and the likes. So this manganese ore will be preheated to 600 and fed into the SAF as usual. Then we have the coke and the fluxes being fed into the kiln, into the furnace. Then we add energy to melt the reactant so that we can get our product, which will be Mn alloy, some slag and some gases. One may ask, if you remember in the title, the presentation was about decrepitation. One may ask, what is decrepitation? Decrepitation is essentially the disintegration or the breakage of solid particles upon heating. This formula here shows us how decrepitation can be calculated mathematically. You have a sample which you preheat, and after preheat that sample and you let it cool, you screen it, you'll get particles that are greater than -6 and less than -6 particles. This M1 here is the mass of the particles that are less than -6, that are less than 6 millimeters after preheating. And this M3 is the total mass of the sample, meaning this mass plus this mass. Then you multiply by 100, then you get your Di -6 in percentage. One may ask, is there really a need to do the research to research this problem of decrepitation in a rotary kiln? Yes, there is a need. The way the SAF works, it doesn't work properly if it is fed fines. What I mean by fines, I mean particles that are less than 6 millimeters. So this current process, the ore has been screened for particles that are less than -6, and we only feed particles that are more than 6 millimeters. Now, when you preheat this ore, there's a question that arises that will this ore decrepitate? And if it decrepitate, how much of it will it decrepitate? And what problems may we experience in the SAF if we feed these fines? Feeding on fines in a SAF has a number of problems. One of them is the efficiency of the SAF. As you know, when the slag, I mean the ore, the fluxes and the coke, they smelt at the bottom of these furnaces, there'll be some reaction. These reactions will produce some gases, maybe carbon dioxide and carbon monoxide. Carbon monoxide, when it moves through the burden of the material, as the gas escapes into the furnace, this carbon monoxide may produce some pre-reduction of this ore, leading us to utilizing less coke in this process. But if you are feeding fines, that bed of minerals won't be gas permeable. In other words, the gas will not be able to escape properly through the bed, and we may not have a sufficient pre-reduction, meaning that we'll use more coke than we're supposed to. And the other thing, if the gas bed is blocked enough, this gases that is being produced at the bottom will accumulate and accumulate. Eventually, we'll have an explosion that is a safety hazard. Then this research had 3 research questions. We wanted to know, how does a varying the temperature at which we preheat this manganese ore will affect the decrepitation index. We wanted to know, how does varying the rotational speed of the kiln will affect the decrepitation index. And finally, we want to know, how does the size range of the ore that is being fed into the kiln affect the decrepitation index of these ores. We'll go a bit into the literature review. There were a number of studies done in the decrepitation of manganese ore, but we found that these 3 here, they are the most relevant. We studied the decrepitation index of 4 manganese ore. These are the 4 manganese ore. We have the uricum ore, the morodamina, azure, and wessel. This is the typical mineralogy of this ore, and this is the decrepitation index they got into the study. The study revealed that decrepitation of this ore that were studied in the study, they were mainly due to the decomposition of cryptomalin at 500 degrees Celsius. Then, if you can go back here, you can see that the uricum ore and the morodamina ore, they have like a slightly less than 50% content in mineralogy of cryptomalin. Hence why we see that the decryptation index are almost similar. Then the other thing is the phase transformation of pyrolusite to be expired at 700 degrees Celsius. Transformation mainly means that a certain mineral is transforming into the other mineral. And this transformation leads to volumetric changes that induces cracks that lead to decrepitation. And we also have a transformation of brownite to osmanite. If you can go back to the mineralogy here, we can see that the Wessel's ore is mainly composed of brownite. The transformation of brownite is the one that contributed to this highest decrepitation index of the Wessel's ore. That's why you see that this ore has the highest decrepitation index. Then we go to physical properties. One of the physical properties that affect the decrepitation index of this ore is the moisture content. This ore, they differ in terms of porosities, and some pores within these particles may be closed pores and others may be open pores. Now, you may have moisture trapped in these closed pores. When you have moisture trapped in this closed pores and you heat it, obviously the vapor pressure of that moisture in the closed pores will rise. Sometimes as the ore is being heated further, the vapor pressure of that moisture in those pores may rise high enough to cause rupture in these particles and have porosity. Generally, like ores that are more porous, they are weak. They can easily break at a lower vapor pressure. Let's say maybe we have the same ore with same moisture content, and some of the moisture is trapped into the closed pores. Obviously, the ore that is weak, it will rupture at a lower vapor pressure compared to the ore that is strong. Then we move to decrepitation in rotary kilns. Decrepitation in rotary kiln is mainly affected by two factors. We have the tumbling action, which is the movement of the particles in the kiln, and you have tumble time. But in this case, since the residence time has been kept constant, we'll only be focusing on the tumbling action that happens inside the kiln. This tumbling action can be further divided into three mechanisms. We have abrasion, which is a process where two particles of the same size that are rubbing against each other when the kiln is moving. This friction that is caused by them rubbing against each other may produce fine. Then we have attrition, whereby we have two big particles rubbing against a small one to produce fine. And finally, we have the impact mechanism. This impact mechanism is mainly due to the collision of the all particles with each other, or the collision of particles with the wall of the rotary kiln. Here you can see that we have zones where this mechanism they usually occur. Here is the impact zone where these particles are colliding with each other. Here we have the attrition and the abrasion zone where these particles are rubbing with the walls of the kiln and are rubbing against each other. We'll now move to the methods. We sourced three types of ores for this research. Then we labeled them OA, OB, and OC. Approximately 200 kg of each ore was sourced. This 200 kg was taken through screening to get these three size ranges. These three size ranges were then taken for coning and quartering so that we can get 10 kg samples, which will then be taken to a rotating splitter so that we can further split them into 1 kg samples, which we are going to use for the decrepitation test, and take some for the characterization. The S received ore was taken for this following characterization techniques. We have ICP-OES to determine the chemical composition, we have the quantitative XRD to determine the mineral present and their quantity. Then we took them for SEMEDS to determine the texture and other properties. Then after preheating this ore, the sample was then taken through for the same characterization techniques. Then the S received samples again were then tested their physical properties. We did a helium pignometry to determine the porosity of this ore. We also determined the loss of ignition. We also dried these samples overnight to determine the moisture content, and we determined the bulk density. This bulk density was determined per size range. Remember, we screened the samples into 3 size ranges, which was +6, -20, +20, -40, +40, and -6. So we determine, let's say for OA, we determine the bulk density for +6, -20. Then again, we determine the bulk density for +20, -40. Then the same applies with +40, -75 millimeters. This here was our experimental plan. All those 3 ores, or A, B, and C, we mentioned before, they were taken through this experimental plan. We investigated the effect of temperature, investigated the effect of rotational speed, and we investigate the effect of size range, as we mentioned in our research questions earlier. When we were investigating the effect of temperature here, the rotational speed and the size range were kept constant at 6 RPM and the size range at +6, -20 millimeters. Here we have the typical cross-sectional view of the kiln that we used in these experiments. Here, as you can see, we have the rotating tube of the kiln. We have the heating elements here. Then here, number 2, we have some insulation to prevent unnecessary loss of heat. Here we have a DC motor. This DC motor is used to drive the rotation of the kiln. This D motor has a knob which you can turn either clockwise or anti-clockwise to adjust the rotational speed of this kiln. Here, this is the experimental procedure. Firstly, we switch on the kiln, power and the rotation, and we put the set point temperature. Depending on the test, maybe 600, 800, and 1,000, as we have seen in the experimental plan. And this kiln was allowed to heat so that it can reach the temperature that was inserted into the controller, which may either be 6, 8, or 1,000. After the kiln has reached the desired temperature, 1 kg of the manganese ore was fed into the kiln. Then the sample was left to rotate and heat for 30 minutes. After heating, the sample was then allowed to cool inside the kiln overnight. Then the following day, the sample was removed from the kiln. Then we screened this sample to get particles that are less than -6 millimeters to determine the decrepitation index. Now we get into the result. Remember, we said the untreated samples were taken through to determine physical properties. Here we have the result of the moisture content. You can see that OA is the one that had the most moisture, and these are the porosity results, which are reported in cubic meters per gram. We have OA, which is the most porous, and the loss of ignition. You can see that for OA we have like a lot of material that is being lost during ignition when we are hitting this material to 1,000. Here we have the bulk density result. As mentioned, this bulk density was mentioned per size range. We have OA, which we did the bulk density for +6, -20 millimeter particles. We have it at 1.6 gram per cubic meter. Then as you increase the size range, you can see that the bulk density decreases, which is expected because as you increases the size range, you know that your particles, they become bigger and more bulky, and they're more, if you put them like in a certain volume, as we did in this test to determine the bulk density, we'll have the particles having more spaces between them. This here is the chemical compositions of the ore that we used in this study. We have A, B, and C. You can see we are reporting the manganese content of this ore. Here is the iron, is the calcium oxide, have the silica oxide. You can see that B has the highest content of manganese at 39%. We have iron content being the highest in OA by 5.5, and we have calcium oxide being the highest in OA. Then we have the silica dioxide being the highest in OC. This is the mineralogy of this ores that we utilize in this study. From this result, you can see that the main source of manganese from these ores, you can see that mainly comes from brownite, haussmannite, and kutnoharite. As mentioned before, we did a characterization of the samples after we taken them through the kiln. Here we have the mineralogical changes in OA that is being heated. We can see that when we have haussmannite here, is increasing when you are moving from 600 to 8, and it's further increases when you go to 1,000. We have kutnoharite here. It's dropping from when you are moving from 6 to 800. Like in this case, kutnoharite drop to 0, because if you remember, the literature revealed that kutnoharite decomposes at 700 degrees Celsius. So it makes sense that here we literally have none of kutnoharite at temperatures above 800. Then we have calcite, which is rising from 6 to 800, surprisingly, because mainly it is not decomposing. It is being produced from the transformation of certain minerals. Then at 800, we have it dropping to 0 because it's being decomposed. And the same here, we have dolomite decomposing. We have maracite being produced for OA. And this here is the mineralogical analysis of OA. We have haussmannite once again rising. We have kutnoharite dropping. And we have brownite dropping. And once again, we have calcite again rising and dropping again. Then we move to OC. Once again, haussmannite is increasing. Brownite increased a little bit and dropped. We have calcite dropping. Then we go to this decrepitation index. Remember, one of our set questions was to find out how does temperature affect this decrepitation index of this ore. Here we have OA, we have a 600, we have a 800, and 1,000 here. As you can see, as you increase temperature, you have the decrepitation index of particles that are less than 6 millimeters increasing. Same applies with OA, and same applies with OC. Then we go to the effect of rotational speed. As you can see here, the jumps in the effect of rotational speed is not as significant as the jumps that we have seen in the effect of temperature. So the rotational speed that does have effect on the DI, but it's not as much as the effect that we experience during the effect of temperature. For the, you can see that for it's the same thing, increasing the RPM. We have 3 here, 6 and 12 here. You can see that the DI is increasing, the same applies to OB and OC. And now we come to the effect of size range. The effect of size range is a different ball game together. As you increase the size range, we have DI increasing for all this. And once again, the difference is not as significant as the difference that we observed with the effect of temperature. Then now we move to the discussion of the effect of temperature. As mentioned earlier, that temperature increases the decrepitation index of this ore. Now the main question is why? Why does increasing temperature increases this DI? One of the reasons is due to the decomposition of quinoharite, which has this ideal composition. This quinoharite decomposes at 500 degrees Celsius. And if you remember, if you can just go back to the mineralogy here, OA has the highest content of quinoharite, which is why here we have OA being the one that is more susceptible to decrepitation because of this quinoharite content. And as you know, like as you raise this temperature, the decomposition of this quinoharite intensify with the increase of this temperature, which is why one of the reasons why the DI increases as you increase the temperature. One other reason is the transformation of brownite into hasmonite at a temperature of 600. If you can remember, you can go back to one of these graphs. As you can see, brownite is decomposing, hence why it's dropping, and hasmonite is being produced from this transformation of brownite, hence why we have hasmonite increasing. This transformation is one of the reasons why the decrepitation increases as you increase temperature, because as the temperature has been increased, this process of transformation of brownite into hasmonite intensifies. Then one other thing you need to know is that brownite and hasmonite, they have different crystalline structures, which means if you have brownite transforming into hasmonite, you have a certain mineral transforming into the other. You have a change in crystalline structure from one structure to another structure, meaning that there is a volumetric change when this minerals transform, when brownite transform into hasmonite. This minerals change is the one that is responsible for the formation of these cracks. Here we have OA that is being treated at 600. You remember that this transformation happens at 700. So that is why here you see that there aren't many cracks, because there's barely a transformation of brownite into hasmonite, which causes cracks. Here at 800, you have more of this brownite transforming into hasmonite. That's why you can see that here there's a slightly more number of cracks that happen due to this transformation. Then when you go to 1000, you can see that the cracks are even more, like because of this the transformation of brownite had intensified. Here's the discussion about the effect of rotational speed. As mentioned in the literature, the main factors that affect the decrepitation is the tumbling time and the tumbling action. Tumbling time in this case won't be focused on, since the tumbling residence was kept constant at 30 minutes for all the experiment. So we'll only be focusing on the tumbling action. We have abrasion, attrition, and impact, which are mostly responsible for causing the production of fine when the sample has been tumbled in the rotary kiln. Here, as you can see, if you remember from the result, we have OA, that is being the one that was most porous, which is why we have it having the highest DI compared to the other ores, which makes sense. Then the other thing is the frequency at which these particles collide with each other or the walls of the container. In other words, it's the frequency at which this breakage mechanism of impact happens. If you have the rotary kiln rotating at the speed of 3 RPM, the probability of these particles that are being calcined in the kiln colliding with each other and the walls of the container is very much lower than when you have the RPM of 12. So this is one of the reasons why you have a higher DI at higher rotational speed. Then we go to the effect of size range. The effect of size range, if you can think about it, let's say for argument's sake, we have 3 samples here that weigh, both of them, all of 3 of them, they weigh 1 kg, 1 kg, 1 kg. If you had the time to count the number of particles that are available in a sample, in a 1 kg sample that with a size range of +6 -20, add a number of particles that are present in a 1 kg sample of +40 -71. Obviously, you will have more particles in a sample that is of the low size range, which is +6 -20. So when we have more particles, once again, we go back to the probability of this collision. If you have more particles in a sample, the probability of these particles colliding with each other to produce fines due to the mechanism of impact is much higher than when we have fewer particles. In other words, the frequency when we have more particles increases, and the frequency decreases when we have a lower number of particles. As you can see here, as it is expected, when you have a higher bulk density, which means you have smaller particles that are not as bulky, which is why we have the higher decrepitation index. The same applies to O, B, and C. Then the other one, when you have bulky big particles, the area of contact between this individual particle is smaller when you have bigger particles, and bigger when you have a smaller number of particles. In other words, if you have a higher number of particles, these particles have a bigger area of contact between them, which will then produce fines due to the first 2 mechanisms, which were abrasion and attrition. This is why the DI decreases as the number of particles decreases, because the area of contact reduces and there's less friction between particles. Then less fines will be produced due to attrition and abrasion. Then when you go to, let's conclude now. We established that temperature increases the DI of all these 3 ore, and this is mainly due to changes in minerals. We have other minerals decomposing, like putnorite. You have other minerals transforming into other minerals, like brownite transforming into osmanite. This mineralogical changes is the main factor that contribute to temperature having the effect on the decrepitation index. Then we have the increase in rotational speed, increases the DI as you mentioned. We increases the frequency of collision between the particles and each other, and we increase the frequency of particles colliding with the walls of the container, hence increasing the DI. Then increasing the size range, decreasing the DI of MNOs, which is mainly due to a reduction of the number of particles as the size range is increasing, which is, and also the other reason is the reduction in the area of contact between the particles and the walls of the container when the size range increases. Here we have references that were mentioned into the presentation. And do we have any questions?
Good, thank you, Sam. I think we asked for questions. If the audience have questions, please write your questions in our question and answer section. You'll find the button here at the bottom of yeah. So the first question is from Happy Malindi. What was the physical structure of the decrepitated ore? Did it have some porous structure, like similar to sponge iron, or as already seen when produced in the direct reduction kilns? So I don't know if you can really comment on the structure of sponge iron, but I think you can maybe expand a bit. You did show us that SEM micrograph, Sam, but maybe just expand a bit on that discussion.
Okay, from the result we got from the SEM, you see, we didn't really notice much pause per se, but what was obvious, it was the presence of the cracks in these samples. So when this also was taken through the kiln, you can see that when you had temperature, we had much more cracks on the samples. But in terms of ore, I don't think there was any changes in terms of, I don't think the ore became more porous after it's been taken through the kiln, just that it had more cracks. It had more cracks than the initial sample.
Yeah, I think there was not, the intention was not to have reduction reactions, so it makes it a bit different from sponge iron production. Then, thank you, Peter Cox from Norway. Very nice presentation. Thank you, Peter. And then he has a question also. Did you make a test at ambient temperature to differentiate decrepitation from attrition or abrasion? So did you run your experiments just at room temperature, your tumbling tests?
Yeah, we did do a bit of tumbling tests on this ore. But the formation of fines like wasn't that much. All this ores, they had like the number of particles that we had that were less than 6, all of them were less than 5%. Maybe we had an increase from 1 to 2.5. Then when you move to 12 RPM, we have like something like 4% of these particles being less than 6 millimeters. Yeah, we did do that.
So this is definitely a temperature or a temperature dependent phenomena. Yeah. Okay, then from Robert Cromarty from University of Pretoria, the influence of particle size is a bit unclear. And then he has a follow-up comment or question. The mid-size range seems to have a higher decrepitation. How is this explained? So maybe just go to that.
Okay, we can go here. Do you say, what did you say, which one has the highest decrepitation index?
Or B.
Or B.
Yeah, okay.
Okay, we can go to these physical properties here. B, as you can see, I don't know how to put it, but B, it was like, even though it was not the most porous, it had, let's go to the mineralogical content. As you can see, B also had like some brownite, like had the highest content of brownite compared to the other three. So the reason that B may be having the one of the highest index when it's being when the size range is being investigated may be due to this transformation of brownite. Remember, like this, when we investigate like the effect of rotational speed or the effect of size range, doesn't necessarily mean that the mineralogy will be taken out. One of the reasons why OB may have like the highest DI may be due to this high content of brownite. You can, if you can check, we said that brownite like transforms at 700. If you look at this graph, you have a much steeper gradient when you move from here to here. This is generally because it is transforming the brownite. I don't know if that answers your question.
I think if Robert will definitely want to continue this conversation with you in person.
Yeah,
but luckily he's local. Then Paul O'Shaughnessy, I think Paul, are you joining us from the UK? He just wants to see the references again. Paul, the SIMM will distribute this presentation as well, so you will receive a copy of the presentation in due course. Then Peter Cox again, did you evaluate the effect of a rotary furnace diameter on fines production?
No, we didn't. Because
Not
like
yet.
doing that, nah, not yet. Because
Yes,
doing
not
that
yet.
will actually like require us to manufacture another rotating tube of different diameter. But that's definitely like something that we can investigate, provided we get the funds.
And also, we are going to run a pilot scale rotary kiln towards the end of the year, and it might be a very good idea to do some of the experiments, repeat some of them there. So thank you for that question, Peter. Then Harman Ottertum from Germany. Thanks, Sam. Good work. You had some graphs where you showed the change of mineralogy with increasing temperature. Have you compared the practical results with, for example, FactSage to see how well theory and reality match?
No, I haven't done that. But that's definitely something that is worth exploring. So yeah, thanks. I'll definitely explore that.
I think, Arman, just to comment on that, the FactSage, the manganese minerals are really complex, and in terms of mineralogy, and FactSage databases don't contain a lot of the phases, but I do think horsemanite and braunite are in there, so it would be interesting just to run a few calcs. Then if I just go through the comments section. Tish is from Internew. Interesting work and results, Sam. Thanks. Your results show that there will be significant generation of fines in the ore studied. How can generation of fines in the pre-treatment unit be minimized? And what is the strategy with regards to utilization of the generated fines prior to feeding the SAF? I presume you wouldn't want to add fines to your SAF. You want to comment on that? Good questions.
Yeah, actually, like in terms of like stopping the generation of these fines in the kiln. There isn't really much that can be done. All we can do at this point, because like we have a specific temperature that we want to feed this ore into the kiln. There's a certain temperature. The only thing that we can adjust in this case, we can adjust the rotational speed, even though the effect is not that much as the one that is caused by temperature. If you operate at low rotational speed as possible, you can definitely reduce the number of fines that you do. Because one other thing, like the mineralogy that we did on the as received sample, we can see that certain or with certain minerals are more susceptible to decrepitation. One other thing you can do, like you can select or to use in this process that contain less of quinoarite and contain less of brownite. I know that you don't really have much choice of that, since like we don't control the content of these ores. But if you have an opportunity to select the ores that you'll be utilizing in the process, I'll advise selecting ore that contain less quinoharite and brownite, which will in turn reduce the formation of this fire.
I think maybe just to follow up on that is we do see that temperature does play a significant role. So it is something that, and from Sam's work, we understand it is due to the phase transformations that take place. So it is important to work with as low as possible preheating temperature. Then, in that sense. And then also to minimize the energy losses from the unit that you preheat into the furnace, because then the temperature at which you need to preheat will be a bit lower. So I think that is one of the challenges in the pilot campaign. We don't intend to remove the fines, so that would be have a screen in between. We don't do that. I think we might be the understanding of decrepitation within the submerged arc furnaces. I think what this study highlighted is maybe that we don't understand that so well either. We might be, I think this one furnace that I have experience with was a silica manganese furnace, and we did see a lot of fines. We thought that was just due to the cooling of the furnace, but it might be that it's actually part of the operation. So I think Sam's work is not the only work that was done on decrepitation of the ore on this project, and I think that's the knowledge, new knowledge that we gained in terms of decrepitation of the ore is one of the spin-off advantages of the PREMA project. Then Marcus RW, thanks for sharing your work, Sam. Keep it up. Are you planning any larger scale test? That does answer my question. Okay, there you said. So I did answer, we did answer the question. We will do a larger scale test, and it will be also on the continuous operation where Sam's was a batch operation. Robert commented another question. The method you use would have resulted in a high heating rate. Do you think the heating rate would have had a significant effect on decrepitation?
Yeah, the heating rate will definitely have the effect on the cause. If you hit these ores at different heating days, there's a possibility of thermal shock. That thermal shock will in turn cause the DI to be higher. So yeah, the heating rate will definitely have an effect on the DI, which is one of the effect that you wanted to investigate initially, but unfortunately, due to the safety measure installed on our kiln, we cannot hit the kiln while it's not rotating. And if you do rotate it, remember, if you use a different heating rate, it means this sample will take different times to get to the desired temperature. Then if they take different time to get to the temperature, this now brings a time, the residence time in the kiln. to play effect and to do the air. So we decided to leave it out for now, since we can't investigate the effect of heating this on its own without bringing in the resident time into the play.
But Robert, this can make a really nice fourth year project, especially you don't necessarily need to rotate. You don't necessarily need to do these experiments in a rotary kiln. So it might be something you can do in a muffle furnace. And if you have a student, then maybe we must have a chat. I think this will be a very interesting fourth year project. Then Quinn had asked a question where he says, thank you, Sam, very nice presentation. With this knowledge, will you be able to predict and advance the degree of decrepitation of any particular ore? Wow. Presumably, this would help with blending and mix management. And then his follow-up comment was, I think this has been answered already. But do you want to comment on that?
Yeah, we can definitely predict the behavior of other ores if you look at their mineralogy, because you know that decrepitation is mainly due to decomposition of certain minerals and transformation of certain minerals. So if we know that these are the minerals that decompose, these are the minerals that transform into certain minerals, we can definitely predict the decrepitation index of other ores. Although it may not be accurate, but you can get close to the true value.
Probably if you do a lot more experimental work, I think that is like a holy grail for us. But yes, I think one can spend the rest of your life just studying decrepitation. Yeah, okay. Then Robert says, we'll chat about this offline. And Armin, inspired by the question of Peter on kiln diameter, would it be worthwhile to investigate impacts separately? The faster a kiln goes, the larger a diameter is, or the more variation in kiln feeding. This means material will reach higher in the kiln and fall a larger distance. Maybe size reduction caused by impact would be simulated by dropping ore from various heights in a vertical test stand and then compare this to impact size reduction inside a kiln. Want to comment?
Yeah, I do agree. Like the longer the distance that these particles have to fall, the higher they will have the number of fines generated through impact. So yeah, I do agree, but I'm not sure about the part of it being worthwhile. That's something that you have to investigate. You have to investigate
Well,
like
think about it. Yeah.
yeah, we'll have to investigate if like this changes like will have like a lot of impact on the DI. That's something that it can be investigated. Yeah.
And Herman's response is a good reply. Thank you. Okay, I think that is it. Yeah, we've had filled our hour. So, thank you, Sam. This was really well done. I feel so proud of my students. and you did really well. Thank you for that. And thank you to the audience also for the nice discussion afterwards. I think it always helps to be able to discuss your work with others. So thank you also for everybody to be in attendance and to the SIMM for this opportunity. This is now the end. See you at the next presentation. Bye.